Good afternoon and welcome to the 28th Annual Exhibit of Hydrogen and Fuel Cell Technologies. This is not the first time I've talked with my next guest, who's Dr. Gunther Kolb, Head Division of Energy at Fraunhofer IMM. We've done this several times before, but there's always something new. Today, we'll be talking about logistic hydrogen carriers for a sustainable future. Yeah, welcome, Dr. Gunther Kolb.
Oh, thank
you. The first question, because so many roles are fulfilled by Fraunhofer, is what is Fraunhofer, and particularly Fraunhofer IMM? Could you tell us a bit about the organization?
So Fraunhofer community is the largest community for applied research. Most of you know it, or in Europe. So our institute is one out of 78 institutes. We are located in Mainz, and we are working in the fields of chemistry, of diagnostics, and also of energy. So the name of the institute is Institute of Microengineering and Microsystems, which means use microstructured components to make practical solutions for our customers.
Now, that's the technical side. When we get down to the nuts and bolts of our transitioning towards renewable energy, we can start with the problem of renewable energy. That is, the more renewable energy, the less the grid, the electrical grid, is capable of absorbing all of it. And we run into the problem of hydrogen, which can be created from renewable energy. What to do with it? Where do you go with hydrogen? And the issues that are involved in the optimal utilization of renewable energy. Let's talk about that and how that relates to what you do at Fraunhofer. The general picture, please.
Yeah, so there are two issues. The one is you, for example, you produce renewable electricity from photovoltaics, but that is a peak power, yeah? So sometimes the sun is shining, sometimes not. You want to store it. You can store it as hydrogen, but that is not the optimum option. Yeah? So you can store it also in the form of chemicals, and that could be, as you perhaps know or heard already, that could be methanol, that could be ammonia, and that could be also synthetic hydrocarbons to utilize them in aviation, because long-distance aviation might need hydrocarbons combustion for propulsion for a long time in the future. Then, if you look at this specifically at the German scenario, you will see there might be a lot of electricity production here in Germany, a lot of hydrogen production from electrolysis in future, but it might not be enough. So some experts say it could be maybe 50%. Where should the rest come from? So it could be made in countries where there is a lot of sun. Let's think about Australian deserts or Arabia. Yeah? So they could make ammonia, they could produce methanol out of that hydrogen they make by electrolysis, and then it can be much easier and cheaper transported to a country like Germany. And there you have to transform it back to hydrogen. This is where our technology mostly comes into play. Yeah? So we make hydrogen generation systems, reformers, ammonia cracking or reforming or whatever, decomposition reactors, however, whatever you call them. Yeah? And you have very compact and viable solutions for our customers.
So I see in there two issues. One is if Germany wants to maintain its role as the leading per capita exporting country in the world, it requires energy, and that is a very unstable equation. We've learned this since the war. We have to recover from this dependency, and that requires potentially more energy than we can create through renewables. So we have this issue of how do you transport renewable energy via hydrogen. And what you just said is kind of interesting for me. There's two equations to this. The politicians always talk about pipelines, but pipelines are actually viable first over land, and then second in close proximity to where things are being used. What you just mentioned there is the necessity to transport large quantities of energy from faraway locations. You mentioned Australia, for example, which has this great the center of the country is kind of like desert, and it's a wonderful source of energy there. I wanted to address this question in just a little bit more detail because really when it gets to transportation, you have this equation of efficiency. How do you convert it to another substance? And that's going to lead us into this application dependency. But first, when we talk about hydrogen, you're the expert. Does everyone in the audience understand that you can take hydrogen and add various CO2 or other things? So what are the potentials of converting hydrogen to other consumable energy sources? What are the major ones with their upsides and their downsides?
So if you look at the energy consumption of an electrolyzer compared to such a methanol synthesis or ammonia synthesis plant, you will see the energy demand is a major part is for the electrolysis. And then you can look at efficiencies also. The efficiency is much higher for ammonia synthesis or methanol synthesis than for an electrolyzer, but the absolute energy demand of the electrolyzer is also much higher. So making these fuels or these hydrogen carriers out of the hydrogen using carbon dioxide, perhaps from the atmosphere, using simply nitrogen, yeah? So it's much less an issue, yeah? Both aspects. And then let me also say something about grids and distribution. So we have a huge existing gas grid for natural gas, which might not be so useful anymore in the future, but we could switch that to a hydrogen plus natural gas grid. Yeah? There are technologies on the way. We are also working together with partners where you can separate easily the hydrogen at the point of demand again from the natural gas, and then you can transport both in the same grid, in an existing grid, which even has a capacity of terawatt hours of its hold up. So there are many options which should be looked at, and I say as long as we don't try it out, as long as we don't make substantial efforts to look at the different technologies, we will never learn which is the best application, which is the best technology for which application.
You just mentioned efficiencies, and I have to underscore this note because rarely do I talk to someone who is scientifically informed about the efficiency proposition of converting hydrogen to other ways of transporting renewable energy. That's what we're really talking about, the source of the energy there. And for me, it's been very informative to learn that the efficiency loss in converting it to, and what are the standard conversions to methanol, to ammonia, those efficiencies are so good that it is not a game changer in terms of optimizing the use. But there's another way of looking at this. Once you convert them, there is a natural gas grid, but there's also distribution facilities. In China, we know there's a huge methanol grid. What existing infrastructures in Germany are available already to distribute renewable energy in another form than hydrogen?
As you said, methanol is available at the gasoline stations in China. We have here a natural gas grid. Yeah, we have here a lot of ammonia transportation every day, every night when you live close to a railway. So there is ammonia running by hundreds of thousands of tons. It's transported on the sea, so it's not really a safety issue. Nobody hears about it because nothing happens. Yeah? So as simple as that. Yeah? So we also can further foster the production of biogas. Biogas contains a lot of carbon dioxide already, and we are also working in projects where we convert the carbon dioxide directly in the biogas to additional methane, and that can be then fed into the natural gas grid as additional fuel. I know about American companies, they produce in the north of the United States, they produce natural biogas, yeah, and they feed it in the gas grid the south, they make synthetic methanol out of that. Yeah, it's virtual, but still they feed in as much as they take out at the other side, so they call it green. Yeah, so that's green methanol. One way to get green methanol by using this gas grid. Yeah. So there are many options, and people should think about and not only go in one direction. As my former speaker also said, we need to bundle all these possibilities and not try to exclude and push people out too early. Yeah? So that, as a researcher, I can say nothing more than that. But maybe go back to our technology, our reactor technology.
Yeah. We're going to get to that. I just wanted to add one question that is related to this. We think of our energy dependency on natural gas simply in form of, okay, it's used for heating and maybe generating electricity. But one of the things we need it for, of course, is to sustain the 7 billion people population of the Earth, that is fertilizers. And one of the foundational things in fertilizers is ammonia. So this is also addressing the need for natural gas, or replacing the need for natural gas with a renewable energy. And ammonia plays that role.
Yeah, so the large number of human beings on this planet couldn't live here if we wouldn't have the fertilizers. Yeah, that is clear. It would be limited already, the agricultural production. Yeah? So we make huge amounts of ammonia. And in the past, 80 years ago, it was made by hydropower, by electrolysis. And then the natural gas got so cheap that these companies in Norway, for example, they stopped it and they switched to natural gas because it was so cheap. Now they are switching back. Just to say that all this technology was already a long time ago available. So,
yeah, no, that is an important message, because indeed many countries were doing things with hydrogen 80 years ago and then stopped because of the incredibly low price. We've now paid the price for this dependency, yes, of course, because it can be turned off, and the backbone of our industry would suffer from that. But let's get to the core technologies that you offer, because they are key. We need cutting-edge systems in order to deal with renewable energy. What are the core technologies that you work on?
So we can offer our customers a whole portfolio of services. We can do studies looking at the technical options, process simulations, yeah? and then we can tell about size and price of these systems. Yeah? You can make comparison, and you can even make life cycle analysis looking at the sustainability of the entire chain of the process. And then the systems we are building, they are decentralized systems, for example, for transformation of methanol to hydrogen, or of ammonia to hydrogen, or we can make such biogas methanation plants, from CO2 to natural gas. Yeah, so, but the core is always a chemical reactor, and many of the applications I was just mentioning before, they are mobile, and therefore we are focusing on catalysts. They are catalytic processes, and you need catalyst and fixed bed reactors, which is the normal technology for a chemical reactor in chemical industry. They are not suited for mobile applications. And this is the reason why you have a catalytic converter in your car. Yeah? So this is a ceramic monolith coated with catalyst. And similar things we are doing, yeah, because fixed bed catalyst is not suited for mobile applications. There will always be attrition of the particles, and then you have contamination with the catalyst downstream. All that we can avoid by using our coating technology. And we have our own catalyst development for each of the process steps. A catalytic coated converter, a reactor, is something different than an industrial reactor for an industrial process. And therefore we optimize the catalyst for each of these. For example, for methanol synthesis, we have developed our own highly active catalyst. And this makes it feasible that our methanol reformers are more robust and more compact than what you can get anywhere else in the world. And we have our own reactor technology. We use heat exchangers, plate heat exchangers, where we can integrate, when it's necessary, where we can integrate different catalytic reactions, feed the steam reforming with catalytic combustion and these kind of things. You can see it at our booth over there, it's not far away. And we have developed that reactor technology starting from really micro, from 100 watts, up to now systems, methanol reformers with 100 kilowatts. Yeah? So we have really scaled up in the last 20 years the technology, and we make it available to our customers for a large variety of applications already.
And it's phenomenal what you've achieved. People used to talk about efficiencies as the game changer here. And when we were preparing for the talk, we did the math together. We're talking about the efficiency from renewable energy source, let's say a wind turbine, conversion to another gas, not hydrogen, but electrolysis to hydrogen to another fuel, and then consumption in a mobile application. And we got to efficiencies somewhere above 50%. So how does that compare to a combustion engine?
And that depends on the type of combustion engine. Of course, a large vessel, a large maritime has a quite good efficiency, but a normal passenger car is more creeping around 25%, and that's already double. Yeah? And even if you use diesel, that saves already half of the diesel. Yeah? So this is an argument
yes,
for using the reformer and fuel cell technology. Yeah.
And of course, you've got large plants already operating at around the 50 kilowatt level.
Yeah, so we have a natural gas, which could be biogas, of course, in future. CHP system with 50 kilowatt. We are currently setting up a 50 kilowatt hydrogen ammonia cracker with a purification running with a fuel cell. We are building a 50 kilowatt methanation plant for converting the carbon dioxide in the biogas to additional methane, so making 100% methane out of the biogas. So these are some examples. We are working also on methanol reformers quite a lot, also in the 25 plus kilowatt range, up to 100 kilowatt.
So we're going to look into the future for the last question. It's a complicated question, and it's unfair to ask for a short answer, but the complicated question is this. We're beyond what I call the Altmaier epoch. That is, it used to be prohibited to build wind turbines close to residential areas, and this made it impossible to develop renewable energies in just about across Germany. That has all changed. We now have to face the challenge of replacing non-renewable hydrocarbons, particularly those coming from Russia, as fast as we can. This also, though, places the burden of responsibility on the industry and ultimately on the capacity of the technological industry to make the best use out of the renewable energy we are going to reap from this new wind turbine development. Are we capable in Germany of ramping up production of the necessary technologies to optimize the use of renewable energies in the form of ammonia, in the form of methane? Is this scalable, and can it be achieved?
I'm absolutely convinced it's feasible, but we have to start now. Yeah? And if we don't start now, it will be too late at some point in time. 50 years ago, the Club of Rome told us already what will happen. Now exactly this is coming. Yeah? So nobody did anything to move fast in that direction. If we don't start now, it will be too late. Yeah? I'm convinced.
Well, I think this is the reason why Monday on the news they reported on the Hannover Fair and they didn't go anywhere else. They were here. It's a shame we don't have time for further questions, but we should continue this conversation at the booth of Fraunhofer IMM, which is B34, over in that direction. It's always great to talk to someone who knows the math as well as the technology involved in saving us from getting cold in the winter, among other things. I've been talking to Dr. Gunther Kolb, who's head of Division of Energy at Fraunhofer IMM. Thank you, and I hope to see you back next year.
Sure.